All right, we are starting chapter 6. Let's go with it. Let me adjust my microphone here. So we have verifying identities. So as we start chapter 6, we move on to something called analytical trigonometry. So what we really want to be able to do pretty much is to solve equations. It's almost like the fusion of algebra and trigonometry together. Alright, so before we get started with the equations, we're going to do some stuff about identities. So before we even do identities, let's take a whole look about all the different formulas that we have come up with so far. Let's take a look at it here. So if you guys remember from chapter 5, hopefully you guys have remembered the reciprocal identities, right? Sine and cosecant, they are reciprocal to each other. Secant and cosine are reciprocal, and then again cotangent and tangent are reciprocal, and then the other way around. Okay, then you have the quotient identities. Tangent is the same thing as sine divided by cosine, works out to be the same way, and then the cotangent is the reciprocal of that. Alright, and as you go through chapter 6, a good thing to do pretty much is just to have all these identities in front of you. I don't know if you want to print out the slide here, if you want to print out what's in the textbook there, but it's good just to have all these in front of you as you're going through chapter 6. Cool. Alright, so then we have some Pythagorean Theorem identities, and hopefully we've seen those in the previous chapter how that is formed. So Pythagorean Theorem identity. So if you take the y-coordinate, the length of the y-coordinate, square it, and then take the length of the x-coordinate and square it, using Pythagorean Theorem. Remember, our radius has always been 1, so there's that. And then these guys are all variations of this formula right here. So again, just kind of give it to you guys real quickly here. There it is. And just like in algebra, you can move things around. So you can move this cosine over here, and so we'll have variations of the Pythagorean Theorem identity soon. Alright, even odd identities, even odd functions, if you guys remember those from chapter 5. Here's all the different even and odd functions. So whenever you see a negative in the angle, we're going to try to get rid of it by making it a positive angle. So much easier to work with a positive angle than a negative angle. Alright, so the equivalent forms of the Pythagorean identity. This is pretty good to have in front of you here. Sine squared theta. So here's our Pythagorean Theorem identity for sine and cosine. If you were to subtract cosine from both sides, you should get this top formula. On the other hand, if you were to subtract sine squared x from both sides, you get the bottom formula. So these are all the different variations that you can get. So from this equation, you can get two different variations. And from this equation, you can get two different variations depending how you move things across. Alright, again, we'll get to those in just a bit. Alright, so just to work with this whole concept of knowing one and trying to find the other, that's what we wanted to work with, knowing one, trying to find the other here. So if you say that sine theta is equal to 4/5, the question right over here is if you go from pi over 2 to pi, think about a quadrant here, think about a quadrant. If you go from pi over 2 to pi, which quadrant are you in? Remember, we start off at 0, we'll go around the unit circle, and then we eventually wind up with quadrant 2. Okay, so now the question is this. How could I go from sine to cotangent? That's the question. How could I go from sine to cotangent? And if you look back through your identities, you find there is no direct route. There's no direct route to go from sine to cotangent. So now you got to think about, okay, how am I going to get to cotangent? Well, one of the Pythagorean Theorem identities connects cotangent to cosecant, and the question is then, could I get cosecant to be connected to sine? So that's the question. So yeah, I think so. Isn't sine and cosecant reciprocal functions of each other? Absolutely. So okay, so if sine theta is equal to 4/5, that means cosecant theta is equal to 5/4. That's perfect. Now I've connected sine to cosecant, and this formula now will connect cosecant to cotangent. I'm going to put in 5/4. Don't forget it has to be squared. So let's go for it here. Okay, could you have used one of the equivalent Pythagorean Theorem identities? Absolutely. You could have done that too from the previous slide. But let's go for it. I'm just going to do some algebra work here and get to 25 over 16. Subtract 1 from both sides and gets me to 9 over 16. Remember, this guy will change into 16 over 16. So then 25 minus 16 will give you 9, as you have common denominators of 16. Okay, still not it. We still have to take the square root. Now the only question is, do we want to use a positive or a negative? So in quadrant 2, think about this, is cotangent. Is cotangent positive or negative in quadrant 2? And it is negative. All right. Let's do it like this here, plus or minus. We can do it like this, plus or minus, and then you have to decide at this point. You're going to choose the positive 3/4 or the negative 3/4. So because it's quadrant 2, we will go with the negative 3/4. There it is. So we have, at this point, knowing the identities from the previous few slides, pretty much is you can get from one trig function to another trig function, just going through different identities. Okay, that's one thing that we got to know. You can always go from one trig function to another. There's enough identities there to make that happen. All right. So now the question is this: can you go from one trig function to get all the rest of them? And since it's practice problem number 2, most likely you can. So let's go for it. It doesn't really matter which order you go. You can go any which way you like. You can go from tangent and you can find cotangent right away. You can go from tangent and you can try to find something else right away. So don't sort of mind the order. It's a matter of me just pulling things from the previous identities and putting them in. So first things first is which quadrant we're in. We are going to go from pi over 2 to pi. So around the unit circle, this means you're starting at 90 degrees, you're going to 180 degrees. That means x has to be in quadrant 2. Okay, why does that help us? Because we're going to have to figure out the signs for other trig functions as they come up. Okay, so let's go for it here. If tangent is x, cotangent would be negative 2. Again, reciprocal functions, right? Reciprocal functions here. Okay, now the next question is, how can we go anywhere else? Is there anywhere else to go? Yeah, let's use one of the Pythagorean Theorem identities. There it is. We can connect tangent to secant. That's exactly what we want. We're good. Once we get secant, we can go some other places here. So let's go for it here. Let's plug in what we know for tangent, which is negative 1/2 squared, giving us secant. And so negative 1/2 times a negative 1/2 is a 1/4. And everybody should be okay there. We can make this into a 4 over 4 over here. 4 over 4. And 1 plus 4 is 5. So this is 5/4 for secant squared. And we have to take the square root. Again, considering that we are in quadrant 2, think to yourself here, is secant. Is secant positive or negative? In quadrant 2, think about that, and I'm going to say negative. And so we end up with secant of x being negative square root of 5 over 2. Remember algebra, we can split this square root into a top and a bottom, and this bottom becomes square root of 4, which is 2. The top remains a square root of 5. Okay, so let's see what we have here. We have tangent, which we already have, but we have cotangent and we have secant. Now the question is, what can we get out of secant? I think we can do cotangent. Oh, sorry, cosine, right? Cosine is just going to be the reciprocal. Now we've got a little problem here. The problem is we have a square root of 5. We don't have a rationalized denominator, so we have to do a little bit of work here. Something about multiplying through to rationalize our denominator. Square root of 5 on the bottom, therefore square root of 5 on top, which gives us a negative 2 root 5 over 5. Cool. So there's actually 6 trig functions, right? And tangent was given, so that means we need to find 5 more, and we found 1, 2, 3, so we need to find some other ones here. So I'm going to connect cosine, and I'm not sure why I'm doing this again, but there it is. There it is again. What I worked was down there given. I think I ran out of room there. So I did it again just to make sure. Okay, so we're missing cosecant and we're missing sine. So can we take tangent get it to sine or cosecant? Can we take cotangent, go to cosecant or sine? It doesn't matter, any which way. Probably the easiest way is just to do this here. This is the Pythagorean Theorem identity for sine and cosine. This is the one that you will use most often, probably. And so what I'm thinking is plug in what we know for cosine. Alright, we're going to have to square this guy now. So kind of careful, make sure you can square it. So negative 2 times negative 2 is a 4. Square root of 5. Square root of 5 times square root of 5 will just be a 5. And then 5 times 5 on the bottom is 25. So 5 times 4 is 20. And the question comes up usually in class is, Mr. H, couldn't you just use a variation of the one that's already solved for sine squared already? Absolutely, you could have. Yep, you got it. Alright, I'm going to go a little bit of the long way here. So let's move this little 20 over 25 to the other side. So it'll be a subtraction now. So 1. So if you move it over here, and we subtract from 5, which is 25 over 25. 25 minus 20 is 5. Hey, that can be reduced nicely. Alright, and I'm not sure, I probably should have reduced that originally here. Remember, we were in quadrant 2. This becomes square root of 5 over 5. Since we're in quadrant 2, sine is positive there. That's cool there. Alright, and one more little thing is cosecant. That is the reciprocal of sine. So let's flip those numbers over. Have to rationalize the denominator again here. And we get ourselves 5 root 5 over 5, and those guys can cancel. Alright, there it is. So practice problem number 2. What we've found out here is we can take one trig function and we can find all the others. Alright. Practice problem number 1 was we can find, we take one trig function, we can find another one. Alright, there's the final answer for cosecant of x. Okay, so now let's really start with these whole concept of finding identities. So finding identities, or verifying identities, what it really means is you want to change the trig functions to be as simple as possible. An expression that's as simple as possible. That's kind of one way to do it. The other one is you want to prove that the left side is equal to the right side. Okay, so in the beginning, let's do this here. Let's just kind of practice. This is something that probably works 90% of the time. Whenever you see a function like this, cotangent x plus tangent of x is equal to cosecant x times secant x, something that happens, the way we want to simplify these is to turn everything into sines and cosines right here. You want to simplify things, and usually that's what it means. If you can simplify things into sines and cosines and then simplify everything else out, you've come to the kind of like the easiest form. Alright, so let's go for it here. So cotangent. Cotangent is the same thing as cosine of x over sine of x. Tangent is sine over cosine. And then we have cosecant is 1 over sine, and secant is 1 over cosine. That's cool. Okay, so let's see. What can we do here? Well, I think we're going to have to get common denominators, right? This can be multiplied together, and that would be a sine and a cosine. And then what happens for this term, we need to multiply in another cosine. So there's your cosine multiplied in. And now on top, cosine times cosine is cosine squared. Over here, this guy needs a little sine. So sine multiplied to the bottom, therefore sine multiplied to the top gives you sine squared. And these multiplied together is like this. And we usually like to put sine first. Whenever you see cosine and sine multiplied together, yeah, usually sine goes first. Okay, let's see, what can we do this? Let's add it all up. So I have common denominators now everywhere. Adding it all up gives you this right here. And does anybody know anything about this right here? Cosecant squared x plus sine squared x. Anybody know anything like that? That's the Pythagorean theorem. Now, cosine squared theta plus sine squared theta, that's the same thing as sine squared theta plus cosine, right? Cosine squared theta. And these guys are all the same. So that's going to be a 1 right here. So that changes into a big O1. You still have the extra little 1 here. And when you add it together, you get a 2. There it is. So this big expression with 3 different terms inside it with a multiplication, one of the terms really just becomes 2 over sine of x times cosine x. Alright, that's what I mean by simplifying the terms. So, practice problem for us. Here we go. Can we simplify this guy? Now this one's going to be a little bit more complicated, especially with sine, tangents, and secants, and already fractions inside here. So let's see how we can work this out. Right, this one's going to be a little bit more complicated than the example problem. Alright, let me rewrite it here. So let's go for it. Everything changes into sines and cosines. So tangent is sine of x over cosine of x. Secant is 1 over cosine of x. So that's that first fraction right here has changed into all this right here. Again, kind of complicated here, but we'll work it out. Adding to the other side. So tangent again, sine over cosine. And secant again is 1 over cosine of x minus 1. Alright. Let's see, what do we need to do? We need to put these right here probably together. So it's just one single form here. So cosine of x, cosine, right? Getting common denominators over here. And when we do that, the top is still exactly the same, no changes. The bottom now becomes 1 plus cosine of x over cosine x. Again, hopefully you're keeping up. If those that are watching this with the video lecture, if you want to pause me, perfect, that's fine by me. Pause me if you need to. The other side, so we're going to multiply by cosine of x to get common denominators. For the bottom term, the top stays exactly the same, no change. The bottom now has a common denominator of cosine, and on top you have a 1 minus cosine. Okay, now we got to keep doing this to get this all settled in here. Let's see what we got here. So I'm going to have to multiply this guy by cosine of 1 plus cosine of x. I'll multiply this guy by cosine of x times 1 plus cosine of x. So I'm going to try to simplify this complex fraction. Okay, getting rid of the bottom so I can move it up, so I can cancel all this out right here. I'm not going to play with that anymore. So as I do this right on top here, I notice everything cancels on the bottom, just as I planned it, right? On top, though, I see a cosine canceling. So that first fraction really changes into a sine of x over 1 plus cosine of x. Nice. No more complex fractions. That's a good thing. Alright, for the second fraction, here it is, cosine of x, 1 minus cosine of x. Again, all I'm doing is get rid of my complex fractions here. So everything cancels on the bottom, as planned. On top, the cosine once again cancels. I got sine of x over 1 minus cosine of x. Again, pause it if you need to here. I know I kind of ran through that pretty quickly, but the whole point there was just to get rid of any complex fractions. Alright, now we have to get common denominators, so let's go for that one here. So, let me just rewrite what we had on the previous slide. That's what I have here. You don't need to rewrite it unless you're doing the same thing I'm doing, but you're just writing on your own sheet of paper. So, let's go for it here. So at this point, what's going to happen? We need common denominators. So the first one, I need to multiply 1 minus cosine of x. So in this case, oh, you know, I'm missing a little x in here. That's what I missed. It should be sine of x. Sorry, I couldn't. Let me add that in right now as I can. So this should have been sine of x right there. On the other side, I'm multiplying in through a 1 plus cosine of x. So the little blue stuff that you see there, that's the multiplication in. Alright, and let the fun begin. So sine of x has to multiply to here. All the stuff on the bottom has to be multiplied here. So as you multiply the bottom, notice these are, in algebra we call them binomials, right? That are with opposite signs in the middle. So all the middles are going to cancel. So if you do this 1 times 1, that would be a 1. 1 times negative cosine is negative cosine. Cosine of x times 1 is a positive cosine, so those middles are cancelled. Then you're left with just this at the end. Alright, that happens on the other side as well. Same thing, because we should have common denominators. Okay, so sine of x times 1, sine of x. Sine of x times a negative cosine gives you negative sine x cosine x. Over here, sine of x times 1 gives you sine of x, and then sine of x times a positive cosine gives you a plus sine x cosine x. Okay, let's keep on going. Finally, we're going to put this, I know this is a long one here, and I'm going to give you a little hint here, see if you guys agree with me here. That 1 minus cosine squared x is just sine squared x, that's it. Again, look at your Pythagorean theorems for sine and cosine. Alright, and then you notice a little something else here. That cosine times cosine and a negative sine times cosine will cancel, so just these little two signs are the ones that added in. And then, since we have sine squared on the bottom, but we have sine to the 1 power on top over here, these guys will cancel themselves out, leaving you an extra sign on the bottom. So all that big humongous thing with tangent and secant and fractions and all that stuff, in its most simplest form, is just 2 divided by sine of x. That's what we mean by simplifying trigonometric expressions. That's cool. Simplifying trigonometric expressions. We're going to run through this one real quick here. Let's go to this one here. This one is when you are trying to prove that something is not an identity. So in order to prove something is not an identity, you just have to figure out the angle measurement that you're going to plug in so that it doesn't work. Kind of like in algebra, you know, if you say prove that this is not an equation, all you got to do is just plug in some value, show that the right side and the left side are not the same. The only thing with trig functions is that sometimes you can put in angles and they turn out to be exactly the same on both sides. So you have to sort of think through, like, okay, what am I going to put in here so that it's not going to give me the same thing. So I'll just give you a little hint here. 45-degree angles work well. 30-degree angles, 60-degree angles work well. So in this case, I'm going to say that it's going to be pi over 4. It's going to be a 45-degree angle. I'm going to prove that this is not an identity. Cosine of x does not ever equal, or will not equal, 1 minus sine of x all the time. As I plug it in, say cosine of pi over 4 is equal to square root 2 over 2. 1 minus sine of x, which now becomes 1 minus square root 2 over 2. Remember, because sine of pi over 4 is exactly the same thing as cosine of pi over 4, right? 45-degree angles are exactly the same. And if I do that, I get common denominators, and then I simplify, and eventually I look like this, and I say, no way, those two are different. These two are different from another, so you can't do that. Okay, so we've looked at simplifying trigonometric expressions, we looked at proving it's not an identity, and then now we go on to verifying. We have to prove that one side of the equation leads to the other side of the equation, or can be manipulated so that the two equations are the same on both sides. So let's go for it here. Okay, so one little thing you got to think about is this right here. You're not solving equations yet. We'll do that later on in chapter 6. You're just verifying that the left side is the same thing as an identity of the right side. Okay, so this is not solving. You're not going to move anything across the equal sign. You're just going to prove that the right side and the left side are technically the same thing. So let's prove. Let's do this one here. Verifying that 1 minus sine squared x over cosine squared x is the same thing as just a cosine squared x, or a cosine x. Alright, so easy one. Here it is. Notice that the right side is just cosine x. You can't simplify that anymore. There's no way you can simplify cosine of x. Alright, so many times what we do is we try to figure out which is the complicated side, and we're going to simplify this expression just like we did before in order for this left side to be just like the right side. So let's go for it here. So this one, so we take the left side and we're going to simplify it so that by equal signs we get to the right side. So this right here, 1 minus sine squared x, is the same thing as cosine squared x. That's the Pythagorean Theorem identities. And because on top you have 2 of them, on the bottom you have 1 of them, these guys can be cancelled, leaving you an extra cosine of x on top, which gives you cosine of x, and you have proved what you started with. You went from left side and you went all the way to the right side with equal signs showing all the way through using identities. Perfect. We verified that those two are just identities. They mean the same thing. Okay, of course it gets complicated, so let's go for it. How about this one? Let's go with this one. Can you verify that this is true? Okay, so what we learned before with simplifying identities, you usually 90% of the time you want to simplify things down to sines and cosines. If you can do sines and cosines, you're doing great. Okay, let me move this on to the next slide and let's go for it here. So let's do this here. I'm going to start off with the complicated side. The complicated side over here is the right hand side this time. So I'm going to go from right hand to left hand this time. So I'm going to go here and I'm going to eventually wind up with this guy. Let's go for it here. So simplifying everything to sines and cosines. Tangent is good. 1 over cosine is secant, and cosine over here as well. So there it is. Step 1, get everything into sines and cosines. Step 2, simplify. So it looks like we have some work to do on the bottom right over here. Let's multiply by cosine of x, cosine of x. Let's leave the top exactly as is, no changes there. And this is going to be 1 over cosine theta minus cosine squared theta over cosine. Alright, hopefully that was good there. Again, those that are watching this video, you can pause it if you need to. Alright, on the bottom, simplifying that little bottom so it's all one fraction here. So the top stays exactly the same. On the bottom now we have a 1 minus cosine squared theta over cosine. Alright, and then let's go to this. That should be it, is that right? 1 minus cosine squared theta, using the Pythagorean Theorem, will change into a sine squared theta. And then what we do is we call it keep, change, flip, right? We take, let me just write it out first and then we'll go from there. We keep this first exactly the same. We change this division marker or the quotient bar into a multiplication symbol. And what we do is we flip or take the reciprocal of the denominator. That's something we learned in algebra. Alright, cosines are gone, hopefully. Sine are reduced for a sine of theta on the bottom. 1 minus sine theta, and we know that 1 minus sine theta is cosecant theta, and which is what we're trying to prove. In fact, if we want to be really, really technical, let's just say it's cosecant theta over 1. Boom, we've proved it. This time we went from the left side to the right side. Sorry, other way around. We went from the right side to the left side. Okay, let's get a little bit more complicated. So with this one here, let's go with it here. So let me just kind of write it out first and then I'll see kind of what we're doing here. So I'm looking to see which one is the more complicated side, and I'm thinking, you know what, I think I'm going to start off with this guy here. We've got plus signs and all that good stuff. I'm going to figure out if there's any things here. Okay, so this is one of the times. This is the 5 other % of the time where you'll see something that happens here. So instead of rewriting everything in terms of sines and cosines, even though it says it right up here, don't believe it, don't believe it. If you're stuck with like tangent and secant, if you're stuck with those just in the equation, it may be easier just to work with those identities. If you're stuck with cosecant and cotangent, it may be just kind of easier to use those identities to solve the problem. So with this one here, notice what I did over here. I noticed that there's 4 tangents over here. There's 2 tangents. I'm going to factor out. I'm going to factor out tangent squared x. As I factor out tangent squared x, I get myself tangent squared x plus 1. I think this is an identity, isn't it? Tangent squared x plus 1 changes into, boom, there it is. I did not need to change it into sines and cosines. So again, just we'll make sure we have, if you guys see tangents and secants, it most likely is probably easier just to work with those identities. If you see cotangent and cosecant, it may be able to just kind of work those out instead of changing everything to sines and cosines, which would have been more complicated here. Okay, next. Let's go with this one here. And notice that both sides are kind of complicated. So let's start off. Notice both sides don't have sines and cosines either. So what I'm going to do here, I'm going to just change the left-hand side into its form. And here's what I'm going to do. I'm going to take the left side, and I'm going to change it to its like basic form. We good? Just its easiest form. So if I go tangent, tangent is sine over cosine. Cosecant is 1 over cosine. So in its most base form right here, this is the right-hand side, left-hand side in the simplest form. Got it, right there. It's there. Can't simplify that any longer. So now let's do this here. Let's take the right-hand side and let's do the exact same thing to the right-hand side. Let's take that. And let's see what we'll get over here. This one's a little more complicated, but let's go for it here. So we need to get the top to be both sine theta. And when we do that, we get ourselves a 1 plus sine theta over sine theta, cosine theta over sine theta. And again, keep, change, reciprocal. And notice what happens. The signs are gone, and we are left with, hey, what do you know? Well, almost the exact same thing that's on the other side. Let's just move it around. There it is. Okay, so this is a different little approach to do it. So we took the left side, we got it to its simplest form, which is this. Sine theta plus 1 over cosine theta. We took the right-hand side, took a little bit more effort, we simplified it, and we turned out to be, these guys are exactly the same. Okay, so if both of them turn out to be exactly the same, we have proved that those two are identities. And then some students usually ask me, but how's that proved? How's that proved? So we say this, if it's called the transitive property of geometry. That's kind of what we're working with here. If you say A can be or is the same thing as B, and they also say that B is the same thing as C, you have just proved that A is equal to C. So if you got one thing and this little B value right here, and both of them is this little value right here. Oh, sorry. What we had before, which is cosecant. So it kind of says this: if is the same thing as this, and that whole same thing is this right here. That means this whole set is equal to. Okay, anyways, that's just a quick explanation of why we understand those two to be the same. Alright, let's go with this one here. This one, one more other thing that we got to think about is something called conjugates. So let's talk about it here. There's a one extra little rule. Again, you're going to use it infrequently, but we should know it here, is conjugates. So let's start with this first, and then we'll kind of work our way, see what we need here. So tangent of x, cosecant of x plus 1. So first things first, let me kind of just back up maybe just real quick just to make sure we understand what we're seeing here. So remember the little rule that I kind of told you guys here, that if you just see tangents and secants, there's no use to bring them back into sines and cosines. It's going to take you such a long time. So what you want to do is you want to somehow still convert the left hand side to a right hand side. But notice there's no squares over here, right? There's no way to do that. So do you see this little denominator here? Secant x plus 1. Now we know that secant squared x minus 1. If we put a little square on this guy, and if this guy was a minus, then it'll transform into cotangent squared. Well, we're going to use that to our advantage. So conjugates are, again, same exact terms, except the sign in the middle has been changed. That's what we want to do right here. In a sense, we're elevating this to a square form. And remember, you can always multiply top and bottom by the same number, right? So let's go for it here. We're going to select a secant x minus 1 so that the middles cancel, so we have ourselves a secant squared. That's what we want to do out of this. So on top, I have tangent of x times secant of x minus 1. We're going to leave those not multiplied yet. On the bottom, we're going to multiply these guys together. That's what we're going to multiply these guys together. Again, the whole point is to go from the left side to the right side. We want to be able to go from left to right. So this has to change into this. And if we can prove it, we've done our job. So the whole key is right here, the multiplication right here of these two. So on top, leave everything else the same. On the bottom, we're going to multiply this here. So secant x times secant x, secant squared x. Then a minus secant x, a plus secant x cancel each other out, and 1 times negative 1 is negative 1. And then we know this little identity. That is just tangent, I believe. Tangent squared. So on top, I have tangent of x, secant x minus 1. On the bottom, now I have tangent squared x. What's going to happen? Tangents are reduced. And I went from the left side to the right side by using the conjugate. So technically what we did is we just elevated the secant to a secant squared so we can use Pythagorean Theorem identities. And one more other thing we have to do is something called trigonometric substitution. Okay, so this is used in calculus. It is used in calculus in order to get an equation or an expression exactly the way you want it. So again, this is kind of just a practice. Like, why are we doing this? It's a practice for something you're going to do in second semester calculus. That's what this is right here. So we're going to do this. We're going to replace x with cosine theta in this expression, and then we're going to simplify it. We're going to simplify as much as possible. The condition is we're looking at a rotation of a unit circle from 0 degrees to pi over 2, which kind of means quadrant 1, right? So let's go for it here. This is the example from the textbook. We go from here, change it into cosine squared theta, and we have a Pythagorean Theorem identity that says that's just going to be sine squared theta. And because it's positive, we can take a square root of it, which just be sine theta. That's it, and we use the positive side of it because it's in quadrant 1. Alright. Practice problem. Here it is, just a little bit more complicated, not by much. Let's go for it here. So replace x with 3 sine theta. Assuming we are in quadrant 1. Alright, let's go for it here. So 9 minus 3 sine of x, or sine theta, being squared. That will transform that 3 into a 9 sine squared theta. And notice real quick here, notice you have double 9s inside there. So that means what we're going to do is we're going to factor out a 9. We're going to put 1 minus sine squared theta. And by the Pythagorean Theorem identity, we know that to be cosine squared theta. And then we have ourselves a 3 cosine theta. Alright, again, just working with trigonometric substitution. Again, something you will see second semester calculus. Alright, and in the book there's some guidelines of how to kind of think through verifying identities. You can sort of read through those. Don't forget your algebra operations. Have your fundamental trigonometric identities in front of you. Write them out so that you can use them. And here's the thing that we looked at is we want to, and this is on page 577 if you just kind of want to browse through them, but we'll just kind of go over real quick here. Start off with a more complicated side if the other side is very easy, and work from that complicated side to the easy side. Always stay focused on the final expression. You're not trying to prove, you're just trying to prove that the right side and the left side are the same. You're trying to prove an identity, so your focus should be always, what am I trying to get to? Okay, you got some options. You convert everything into sines and cosines. Again, it works 90% of the time. Okay, convert everything into sines and cosines, and you go for it. Other option is you can just, instead of working from the left side to the right side, or the right side to the left side, what we do is you take both sides. You transfer them separately, and you try to make simple equivalent expression. Alright, and third option is use conjugates. And the conjugates are given right here, just so in case you forgot them. 1 plus cosine of x, and then these are all the ones that can elevate your terms to get you into Pythagorean Theorem identities. And then again, there's a whole list of them. So look at your Pythagorean Theorem identities as well.